20-year campaign is not just a goal, it is an engineering requirement for remaining competitive in a global market. So, if we cannot protect the vessel, we cannot maintain the thermal stability required for consistent hot metal chemistry. So, today we are diving into the resilience engineering required to defend the furnace against premature abrasive wear. So, by the end of this session, you will understand the physics of self healing accretion layer, the advanced geometry of stone box, copper strips, and how we use predictive digital twins to extend the campaign life. So these are basically our three topmost agenda out of this presentation. On your screen, as you can see, a wireframe schematic of the furnace, where the neon orange highlight identify critical thermal load areas like Bailey and Bosch, where we have got a max load. So note the blue line represent the cooling water circuits, and these are the veins of our operation. So understanding this anatomy is the first step in establishing the modern cooling standard. So to understand how we achieve this longevity, we must first compare our current technology against the historical evolution of cooling. So coming to our next slide, which is on a evolution matrix, where we are establishing the modern standard. So look at the evolution matrix on this slide, which compares cooling plate, cast iron staves, and modern copper standard. On the far right, the orange highlighted column shows why copper is non-negotiable. Its thermal conductivity is 10 times higher than the cast iron, providing absolute shell protection by withstanding extreme heat loads and primary liquidus. The so what here is simple. Higher conductivity allows for the lowest operational cost and a highly compact design. So while cooling plates rely heavily on surrounding refractory, which is a point of failure, copper strips thrive when near wall ferrous material is pre-reduced and softened. This evolution in hardware allow us to move away from a expensive high maintenance plate system towards a closed loop high efficiency setup. So, however, the real magic of copper is not just the metal itself but the protective layer it creates. So, this high thermal flux is what enables the most critical mechanism in furnace longevity, the self-healing cycle. So focus on the infinity loop on the left side of your screen. So this represents the self-healing cycle where high heat flux solidify liquid material into an insulating accretion layer. When a projection like a body descent is there, it is strip of this accretion, or we can say the healing layer, strip this layer, and the liquefied ferrous material hit highly conductive copper and solidified again within the minutes. On the right, the thermal shield cross section shows the incredible temperature gradient we manage. Follow the level from the right to left. The furnace core is at a staggering 1500 degrees Celsius, yet the copper bodies stay at cool 150 degrees. So thanks to 30-degree water channel, the build-up accretion uh, sitting at 800 degrees act as our primary defense. So maintaining this static layer is only way to prevent the moving burden from grinding away your capital investment. So even with a thermal unsealed, we must still account for the mechanical realities of abrasive wear. So the wear physics, as you can see in this slide. So on the left is see those red arrows pointing down. They represent the massive downward force of jagged body rocks grinding against the exposed orange copper. This is abrasive mechanical grinding. On the right, the matrix identify four critical factors: stave hot face hardness, number one; body material hardness, number two; material pressure, number three; and body speed, number four. Now coming to talk about the operational impact, as you can see, unreduced sinter is twice as hard as unreduced material, meaning poor chemistry in the upper stack directly accelerate physical wear in the belly. High productivity forces more movement against the wall, increasing material pressure at the transition zones. So if you do not control these kinetics, the copper will fail regardless of cooling capacity. So we had to prove this, which led to our accelerated validation trial. To isolate these root causes, we moved from theoretical model to high-speed physical simulation. So, to solve the weird problem, we engineered a real world scale test rig that replicates 5 years of abrasive descent in just 4 months. The central graphic shows a 3D laser scanning system and pressure sensor that measure exerted forces weekly. We use 20 reduced size staves but maintained full scale hot phase featured and used real scale abrasive center. The key finding from this aggressive acceleration was that unprepared material aggressively descending along the wall is the primary root cause of premature wear. By using rotating table extraction, we guaranteed homogeneous wall flow to simulate identical radial wear across the test subject. This data was the catalyst for the complete hardware redesign you see today. We moved from flat surface to complex geometries designed to trap rather than resist the burden. This led to a complete overhaul of stave anatomy to prioritize material stagnation over a simple cooling. These 3D render shows the hardware anatomy of our advanced copper stave. Notice the increased rib thickness and dependent grooves. So these create a rolling effect in the near wall burden, trapping material to stabilize that vital accretion layer. So we have also introduced curved geometry matched exactly to the cell radius to eliminate protruding balconies that act as a high wear target. So look at the protruding steel blades. On the upper edge, these protect the lower shaft while managing uh, high head loads. So we have even added removable nose protectors, wear resistant element that can be swapped from the outside without blowing down the furnace. The so what here is a significant reduction in unplanned downtime and maintenance cost. The feature work together to trigger a specific micromechanism that force the body to protect the wall for us. So look at how these physical features actually manipulate the material flow at the microscopic level. So this slide illustrates two critical micro mechanisms, the stone box effect and the embankment effect. On the left, in a flat section, metallic insert act as a physical trap. Notice how the downward flow in the graphic grind against the trap static rock rather than the copper body itself. So we are making the body wear against itself. On the right, at severe transition zone, we use protruding noses to create deliberate dead zone or embankment. So this embankment completely insulate high pressure areas from the moving burden. Operationally, this means we are no longer rely on the hardness of the copper to resist abrasion. We are using the internal friction of the burden to create a permanent protective barrier. This physical defense is robust, but it requires digital oversight to stay within the optimal operating window. So, hardware is only half the battle. We need the diagnostic core to provide predictive operational defense. So coming to our operational defense slide. So now we look at the operational defense system integrating BF expert and SACM. So follow the data flow from left to right. The bellus top manages burden flow and gate angles for optimized gas distribution. This data fits into the diagnostic core where BF expert runs the thermal status module for live heat load mapping. That bright red spot indicates a thermal spike. The predictive shield then compare this live data against the typical pattern, detecting 185 distinct harmful phenomena before they cause damage. Finally, the warning triggers alert operators to raise the cohesive zone route via thickness probes and skin flow temperatures monitoring. So these allow us to soften ferrous material before abrasive damage occurs, effectively mitigating the risk of stave thinning through proactive process control. So when you combine this digital intelligence with our advanced hardware, the result is a furnace that can outlast the competition. So coming in a concluding slide, the 20 plus years campaign is achieved through the integration of mechanical seal and the operational seal. On the left, we have our hardware curvature optimization and stone box grooves that physically reject unprepared burden. In the center, our software BF expert and SACM ensure that the material arrives at the wall perfectly softened. This result is the ultimate defense, a permanent accretion layer that unlock multi-campaign reuse of your copper strips. So worldwide comparisons confirm that the lowest fuel rate and the highest productivity belong to copper strips when they are engineered as an integrated system. So invest in the resilience of your vessel today to ensure the profitability of your plant for the next 2 decades.